4.1 related rates. The main idea of related rates is that one derivative will be expressed in terms of another. Expressed in terms of, i.e. related to another. A lot of this arises quite naturally through the use of the chain rule, as I'll show momentarily. Let's take a quick example to demonstrate what I'm saying here. The problems in this section are quite diverse. There's not necessarily one methodology to solve them all. How fast, it's a very common question regarding related rates. How fast is the area of a circle increasing when the radius is, I don't know, just make something up, is 25 centimeters. If the radius is increasing at a rate of, let's make up some numbers here, something like 5 centimeters per second. All right, that's a pretty big question. So, first of all, when you look at the question, it says how fast. As soon as you're talking about fast or speed or something, immediately you must think in terms of time. No such thing as quickness without time, right? Every process that has some sort of speed associated with it must have something to do with time. So how fast is the area of a circle increasing? Okay, so what speed with relation to time is the area increasing when the radius is increasing, right? At 5 centimeters per second, and then right when the radius hits 25 centimeters is where we want to look at. How fast is the area increasing right when the radius hits 25? So what are the related rates in this particular problem? First of all, since dealing with the area of a circle, I should probably invoke that formula. So we know that the area of a circle is pi r squared, right? So clearly the area depends on the radius. And you could say the other way, the radius depends on the area. It's also true, right? Depending on which one you actually have in your grasp. If you know the radius, then the area can be determined. If you have the area, then the radius can be determined. So clearly there's a relationship through this equation between area and radius. Now, what am I looking for, though, from this? I'm not really looking for the area and the radius. I'm looking for how fast is the area increasing. So I'm really trying to find, right, how fast is the area doing something. That's nothing other than dA dt. That's the derivative of the area with respect to time, right? The change in the area, right? dA dt sitting there, right? There's dA dt. It's how fast the area is changing, right? Area with respect to time, what is its derivative? Okay, so we're supposed to find that object. We need to find dA dt. Now, if I want to find dA dt using this particular formula, because we're talking about area of a circle and a radius is in here, obviously, so then I need to differentiate this expression with respect to time. Okay? So, since I need to find this mathematical object, and it is a very wise thing to write down what you were trying to find from the verbal description in the problem into mathematics, into mathematical symbols. It's extremely important to be able to do that. It makes the problem much easier to deal with. So I need to find dA dt, so I'll take the derivative with respect to time. So the derivative over here with respect to time is the symbols dA dt. Now if I apply d dt on the right to pi r squared, then the derivative will bypass the pi constant, so pi moves to the outside of that, and it will encounter the r squared expression. Okay? R is not a constant in this problem. As the radius changes, and we said it is changing at this particular rate, the radius is changing, so this is not a constant here. And the area is changing, that's not a constant. So these two derivatives, right, dA dt, and then the derivative applied to r squared are not trivial. Right? They're not zero, per se. Pi is the only thing constant here. Right? There's constant proportionality between the area and the radius. So as I take the derivative with respect to time on r squared, I'm pretending, not really pretending, but according to the problem, r is dependent upon time. Right? As time passes, the radius changes size, which correspondingly causes the area to change in size. So when I take this derivative, I'm viewing r, right? I need to view r as a function of time. So r is kind of like r of t. That's how we're thinking about it. So when I take the derivative with respect to r, when I take the derivative of r squared with respect to time, then I have a composite function here. I have an inner function r and an outer function, the squaring function. So the 2 will come down. So I'll have 2 pi, and then r will now be to the first power, right? Which I'm not going to write, the first power there. But then I will also have to take the derivative of the inner function r with respect to time. And that will be the symbols dr dt.